Hello, welcome to this video 6-5. We're going to talk about the second fundamental theorem of calculus, as well as integration involving the natural log. Without further ado, let's go ahead and look at how the second fundamental theorem of calculus is derived. And we're going to go ahead and start out just with a basic definite integral, integrating from x to 10 of f prime of t dt. Well, the integral of f prime of t with respect to t is just f of t, and we are evaluating from x to 10. So using this, we get f of x minus f of 10. And that is the first fundamental theorem of calculus. Okay, so how does this tie into the second fundamental theorem of calculus? We are going to go ahead and we're going to take a derivative of this. So notice that this structure is exactly the same here. The integral from x to 10 of f prime of t dt. Okay, we already said, hey, that is f of x minus f of 10. Okay, and now we want to take a derivative of this. Well, when I take the derivative of this, this is just going to give me f prime of x, right? The derivative of f of x is f prime of x. And then the derivative of f of 10, that's just 0. It's a constant. The derivative of a constant is 0, okay? And here is the second fundamental theorem of calculus. For any constant a, the derivative of an integral from x to a of f of t dt is f of x. A derivative and an integral essentially just cancel each other out, okay? So we can plug in the bounds. All right, we're going to go ahead and also look at another form, the chain rule, before we kind of go ahead and plug this in. They say find the integral of f prime of t dt from x squared to 0. Okay, so if I integrate this, this is going to be f of t evaluated from x squared to 0, which is f of x squared minus f of 0. Okay? All right, well, what happens now if I was to take the derivative of this? So I'm taking the derivative d dx of, it was f of x squared minus f of 0. Well, the derivative of f of x squared is just f prime of x squared, but I now have to multiply times the derivative of the inside, which is 2x. Okay, and then the derivative of f of 0 again is 0. So I get this format. It's just f prime of x squared times 2x. All right, so hope you can see any connections there. Feel free to pause the video and try to see. But let's go ahead and look at another example, which will help solidify this idea of the second fundamental theorem of calculus. Okay, again, I want to integrate f prime of t dt. We know that this is f of t evaluated from our bounds to x. From x cubed to 2x. So we go ahead and plug this in, and this is f of 2x minus f of x cubed. Okay, so how does this tie into the second fundamental theorem of calculus? Well, let's take the derivative of that. I now want to take the derivative d dx of f of 2x minus f of x cubed. Okay, and when I take the derivative of this, again, I get f prime of 2x, now times 2, times the derivative of that inside function, minus the derivative of f of x cubed, which is f prime of x cubed, times the derivative of x cubed, which is 3x squared. Okay, and if you haven't picked up on it by now, the second fundamental theorem of calculus, whenever I take the derivative of an integral, I end up with the same function. Have you noticed all of these are f prime? I go back to f prime. I can plug in my bounds, okay? Plug in the bounds, which are x cubed. And then in this format, I have the chain of each of these. I have the derivative of the bounds, right? The derivative of 2x is just 2, and the derivative of x cubed, I have to multiply times 3x squared. Okay, this is the second fundamental theorem of calculus, and here is the chain rule version. So this is a problem that you will see often. What's the derivative of the integral? And you should automatically think, hey, these are going to cancel out, but I do need to plug in the bounds, right? And remember, from the first fundamental theorem of calculus, we subtract the bounds, okay, when evaluating. But if I have a derivative, if I have a function that has a derivative, I have to multiply times that. So these examples, they want us to go ahead and find each of the following without integrating. Okay, so let's look at this. I have the derivative, for example 7, derivative of the integral from from x to 0 of 2t minus 3 dt. Okay, well, I know that the integrals and the derivative are going to cancel out, and then I'm going to subtract my bounds. Well, the derivative of a constant function is just 0, right? So my function evaluated at 0, so 0, minus, if I go ahead and now plug in my function, 2 times x minus 3, and there you have it. That's it. That's the second fundamental theorem of calculus. Let's look at example number 8. The derivative of the integral of 2t minus 3 from 2 to 5 dt. Well, again, this is just 0. I'm taking a derivative of an integral. They're going to cancel out. But when I take a derivative, notice these values are constants. When I plug in a constant, the derivative of that is 0. So my answer there is 0. Example number 9. Here I'm taking the derivative of an integral from -1 to x cubed of this function. So again, the derivative and the integral are going to cancel out. But I do have a function here. I'm going to essentially plug this in. So I have x cubed quantity squared plus 2 times x cubed. Okay, and then I'm going to go ahead and multiply all of this times the derivative of x cubed times 3x squared. Okay, and there's our answer. That's it. All we have to do is just plug this in. And in this case, since I can take a derivative of that, I multiply by that. That's the chain rule form. All right, next example here. Here's the same problem, just rewritten in a different format. They say if f of x is equal to the integral of 1 minus t squared to the power of 10 dt from 0 to 3x squared, then what's f prime of x? They're essentially asking you what's the derivative of that integral. So it's the same exact format. I'm going to go ahead and I'm just going to plug in the bounds. So I plug in this here. So 1 minus 3x squared, quantity squared, to the power of 10. And then I also am going to multiply times the derivative of the bound that I plugged in, which is 6x. And that's it. That is, my friends, the second fundamental theorem of calculus. Okay, so here is a practice problem. Pause the video, try this one. Try using the second fundamental theorem of calculus. We're taking a derivative of an integral. What happens? Hopefully you tried it. Here is the solution. So we just get the cubic root of x squared minus 5x. Again, notice all I do, you just plug in a variable in here. That's it. That is it. If you're like, how does that work? Go back to the beginning of the video and watch the beginning of the video. I showed you how it works. We're integrating, and then we're taking a derivative. We're undoing it. So we end up with the variable with the bound plugged into the function that we began with. Okay, here is the next example. But this time, watch out, we have chain, we have derivatives of these bounds. What do? Okay, hopefully you pause the video. Here is the solution. All right. Again, we plug in our functions. but you have to multiply times the derivative of the bounds. Okay, so there you have it. That's the second fundamental theorem of calculus. All right, moving on to the second half of our lesson, we want to talk about integrating using the natural log. So differentiation and integration are inverse operations, and thus if the derivative of the natural log of the absolute value of x is 1 over x, then the integral of 1 over x is equal to the natural log of x plus a constant. As well as if I have the chain rule form of this, if I'm integrating, I'm taking a derivative of the natural log of the absolute value of u, where u is a function of x, I get u prime divided by u, right? 1 over u times the derivative of the inside. So if I want to integrate that, if I'm integrating something where like a function in the denominator and I have the chain in the numerator, that's going to be equal to the natural log of u plus a constant. Okay, so here is the integration rules for logarithms. The integral of 1 over x dx is the natural log of the absolute value of x plus c. And then here's the chain rule form of that. So if you want to integrate a function and it's in the denominator 1 over u, and you have to have u prime, it's equal to the natural log of the absolute value of u plus c. Now note, I have absolute values around my argument for the natural logarithm. Now why is that? Well, I have to make sure that my argument is positive. The domain of logarithms is greater than 0, so I have to make sure. That's why. Okay, so let's go ahead and integrate these examples. I want to integrate negative 3 over x dx. And again, you can rewrite it like this, negative 3, 1 over x dx. Hey, 1 over x. Well, how do you get 1 over x? Well, you differentiate the natural log. Okay, make sure you add in the absolute value symbol there. Integral of 1 over x is natural log of absolute value of x. All right, example number 12. Here I have a lot going on. I have in the denominator p squared plus 1. Now, the derivative of that is just 2p, okay? Well, hey, I have a p here. I'm just missing a 2. So I'm going to go ahead, I can multiply in the 2 here, and then balance it with a 1/2. So here's the hook, right? That's going to go away, and we're essentially integrating this function, 1 over u, with our u prime du. Okay, I guess I should add here 2p dp. So this is equal to 1/2 natural log of the absolute value of our denominator, p squared plus 1, and then we add in our constant. All right, example 13. Alas, we have trig functions. Okay, well, if I let my trig function be tangent of x, well then the derivative of that is secant squared of x dx. So I have my reverse chain right there, and I'm integrating the 1 over u format with my u prime. So I'm going to go ahead, I'm going to integrate this. This is equal to the natural log of the absolute value of tangent of x. That's an absolute value sign there. Plus c. Okay. Okay, a couple more examples. In this case, example number 14, they're being a little bit tricky here. You're going to see the 1 over x and you'll be like, hey, that's my u. U is equal to x. Well, I mean, that doesn't really get you anywhere. It doesn't take care of the natural log of x. So actually, the substitution we're going to make is let u be the natural log of x, and then the derivative of that is 1 over x dx. So I can rewrite this to look like this. Natural log of x times 1 over x dx. And then there's our hook, right? And I'm just integrating the natural log of x to the power of 1, right? U to the power of 1. So this ends up becoming the natural log of x to the power of 2 divided by 2 plus a constant. Right? I just used the power rule there. I'm treating the natural log of x as my function, and I used power rule. All right, next example, example number 13. Okay, here, I hope you see this format, 2 minus natural log of x, and say, hey, that's a lot. What if I can simplify that to be just u? 2 minus natural log of x. And then the derivative of this, du, is equal to, derivative of 2 is 0, derivative of natural log of x is 1 over x. But we do have that negative. Okay? So let me rewrite this to show you what we got so far. So I have 2 minus natural log of x to the power of 3. Then I have my 1 over x dx. I'm missing the negative, so I'll introduce the negative here, and then I'll balance it on the outside. Okay, so here is our hook, right? I have the dx over here. There's our hook. That's going to go away. And essentially what we're integrating here is we're integrating u to the power of negative 3. Negative 3 here. Okay, so this gives us negative 2 minus natural log of x to the power of, if I add 1 here, we get negative 2, and then we'll divide by negative 2 plus c. Okay, and there you have it. Oh yeah, they rewrite it like this. You could have the two negatives, right? Negative, negative 1.5. That makes positive. And then you have 2 minus natural log x to the power of negative 2 plus c. So this would be an equivalent form. 1/2, and then this piece just moves into the denominator. And obviously they make the exponent positive there. Okay. In this example, another question I might get is, why did we not use the natural log of absolute value of the denominator? And the reason is because I didn't treat this whole piece as my function of u, right? My u is not 2 minus natural log of x quantity cubed. I'm using the power rule here. So that's kind of why. If I was to say, hey, my denominator is 2 minus the natural log of x to the power of 3, well, then the derivative of that is a lot more complicated than what I have here, okay? So just if you were wondering that. All right, here is a practice problem. Go ahead, pause the video, and try this one. All right, hopefully you went ahead and tried this one and noticed that your denominator, the derivative of that is in your numerator, 2y minus 3. All you have to do is just go ahead and multiply that by 2. Multiply that by 2. Okay, there's your answer. All right, examples 16 and 17. We're going to go ahead and integrate these two functions by rewriting them as a fraction. So the way that we integrate these, I mean, I don't have a direct, easy, right, simple trig function rule to integrate cotangent of x. I know how to differentiate it, but not integrate it. Well, what we do is we rewrite this using a trig identity. That cotangent is cosine of x over sine of x dx. and we say, okay, I'm going to let u be sine of x, and then the hook-on factor of that is cosine of x dx. So now, when I go ahead and make the substitution, what we have is this format. The u prime over u, and then there's your hook-on factor, okay? So this is equal to the natural log of the absolute value of sine of x plus c. And the same thing for tangent. We're going to use the same tricks integrating tan x dx. I'm going to say, hey, this is sine of x over cosine of x dx. Make sure to bring your notation along with you. Okay, and I'm going to say, okay, I'm going to let u be cosine of x, and then the derivative of that is negative sine of x dx. So I have that here. I'm just missing the negative, so I can add in a negative here, but I better balance it outside with another negative. Okay, so this ends up giving me negative natural log of the absolute value of cosine of x plus c. All right, the last example I have for you kind of formalizes those rules that we just came up with. The integral of tan x dx is equal to negative natural log absolute value of cosine of x plus c, as well as the integral of cotangent of x dx is equal to the natural log of the absolute value of sine of x plus c. I wouldn't worry about remembering these because you can always, if you have to integrate tan x or cotan x, you can use that same formula. But here they want us to use the chain rule form of this, where we let u be equal to 2x, and then the derivative of that is just 1/2 dx. 1/2 dx. What am I thinking? 2 dx. So if I wanted to go ahead and integrate this, I can use the rule that's right there. I just do have to have my chain of 2, and when I multiply in a 2, I have to have a 1/2. So this is equal to 1/2. Okay, the integral of tangent is negative natural log absolute value of cosine of x plus c. I honestly wouldn't expect you to memorize that one. Negative 1/2 natural log absolute value cosine of x. 2x. Because we have a 2 here, 2x. All right, and that is it. Okay, I do have a practice problem for you. Pause the video, try this example. All right, hopefully you paused the video and utilized the inside function y squared as your function. So then du is 2y dy. You're going to have to introduce a 2 and then balance it and use that tangent, integral of tangent rule. So here is your answer. All right, that's going to do it for this video. In this video, we talked about the second fundamental theorem of calculus, where you just, if you're taking a derivative of an integral, you end up with the same exact function, okay? And then we integrated using the natural log of x. All right, go ahead, give me a thumbs up on this video, subscribe. Catch you next time. Peace.